Hello Coursera classmates, this is Garrett and we are doing lab 1 here, which is constant velocity motion. Constant velocity can be found using Newton's second law, or can be measured that way. And there are two main formulas that we need to use for this lab, and that's finding final velocity, where final velocity equals initial velocity plus net force divided by mass times the change in time. And using the final velocity, we can predict positions with final position equaling the initial position plus the final velocity times the change in time. Now for this lab we are doing the movement of a basketball, and here's a rudimentary graph where at the origin is the center of mass. My hand has pushed it towards the left, or the negative x-axis, towards the negative x direction, and it's not moving up or down because it's on the floor, so nothing in the negative or positive y direction. And if we flip the axis over where the positive x-axis is pointing in this direction, it wouldn't really change the values except to change the measurements from negative to positive. So to find where the final velocity remains the same as the initial velocity or has a constant velocity, you need to make it where the final velocity equals the initial velocity plus 0, and the only way to get that when you have a mass and a change in time is to make your net force a vector of 0, 0, 0, where multiplied by time or dividing by mass isn't going to change this from 0, so you effectively have constant velocity. So gravity doesn't really play a role because it's not moving downward, it's on the ground. And air resistance is negligible because air resistance is only applicable to high speeds for any effect. The main two forces is the force by my hand towards the left, or towards the negative x direction, and friction, which is going to be pushing against the force of my hand, which is friction caused by the floor, pushing in the opposite direction towards the positive x direction. And to achieve F net of 0, the force of my hand and the force of friction have to add up to equal 0. Okay, so here's my experimental data with the basketball movement. As you can see, it's heading in the negative x direction, and it seems to be moving at a constant velocity. Over here we can see the table, and with the initial position of negative 0.009 and the initial time of 0, and to find our initial velocity we multiply the second position or final position minus the initial position and divide it by delta t to find your initial velocity, which in this case is negative 1.74. And yeah, and you will see this data later in the end graph. Okay, so here is my theoretical data in VPython. The ball's mass is 0.624 kilograms, which is the average weight in SI units for a man's basketball. The initial conditions, the initial position and initial velocities of the ball are listed here as vectors, and the initial time is 0. And the time steps are 0.01, which allows us to get an accurate reading of the velocity, whether it changes or not. In this case it won't, as it's constant. While t is less than 1.043 seconds, which is the end time for the experimental data, the net force is going to be a vector of 0, 0, 0, and the velocities and positions are determined by the final velocity and final position formulas, and the final times are each equal to the initial time plus the delta t. So here's my final graph. The position is marked in meters on the x-axis, time in seconds on the y-axis. The experimental positions are marked in blue, and the theoretical positions are marked in red. And as you can see, the constant velocity is the ideal red bar, and the blue bar actually does have constant velocity up until 0.6 to 0.65 seconds, where it begins to diverge, probably due to to the fact that friction has begun pushing more than the force my hand inflicted on the ball, causing it to slow down. And so the constant velocity seems to be shown quite well here and up until that point, and I hope you enjoyed the lab.